Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. Now let's look at step 4 of a 4-step travel demand model called traffic assignment. In all the topics in traffic operations, we are going to see through a series of videos. A travel demand model is my favorite topic, and within the travel demand model, trip assignment is my favorite topic. So I can talk through the theory of trip assignment, or also called traffic assignment, for entire day, but I'll try to limit myself on the theory side of things uh, uh, for this video only, and we will look at practical side of traffic assignment in more detail. So traffic assignment is a kind of mathematically pretty intriguing. Like I said, is one of my favorite topic in the field of entire traffic engineering. It's a very nice, very kind of challenging or very intriguing topic to learn. Traffic assignment. It's my favorite topic. So let's get started. In previous videos, we looked at first three steps of 4-step travel demand model. The step 1 is trip generation, step 2 is trip distribution. Then we looked at two different methods within trip distribution. One is growth factor method where the base OD is available, and then we looked at gravity model when base OD is not available and we are using a impedance matrix to calculate synthesis OD. And then we looked at mode choice very briefly. Now we will look at trip assignment. So in this step, a trip between two zones are assigned to various routes available in transportation network. The traffic assignment can be done using two methods. One is user equilibrium and one is system optimization. User equilibrium is a realistic concept that is widely used in practice, and we will look at what user equilibrium is. System optimization is mostly an academic exercise at this time, even though Transcad and other travel demand modeling software provides an option for system optimization. They are barely implemented for practical purposes. So user equilibrium is based on the principle that user would choose the route to minimize their own travel time. So what user equilibrium says that between two origin destination pair, user will always choose the shortest route that is shorter to them. Under user equilibrium, the travel time on all used routes are the same. So that's the first implication of user equilibrium. The travel time on all used routes are same. And if a route is unused, then the travel time on that unused route will be higher or equal to the one on the used route. So for example, let's say I have one origin here and the travel time on route 1 is 10 minutes, travel time on route 2 is 11 minutes, and travel time on route 3 is 10 minutes. Then we can see, let's say route this second route with 11 minutes, there are 100 vehicles. Now these 100 vehicles, what they can do is they can shift to these two routes. Uh, they can shift to these two routes and reach to their destination faster. So what user equilibrium does, it distributes such that under equilibrium, the travel time on all the routes are same. So let's say the more vehicles end up in top and bottom route, so the travel time on all the routes became 10.5. That's kind of a general way of saying user equilibrium. And if there is another route, let's say it goes through different bypass and there is 30 minutes route, uh, so nobody will choose this route. That's another implication of user equilibrium, that if somebody is choosing this route, they can just switch to the shorter route and then arrive to their destination in less time. So either a route is used and travel time on all the routes are same under user equilibrium, or if the travel time is higher, then that route may be unused. So uh, Wardrop introduced the concept of user equilibrium in 1952. So we will look briefly how this user equilibrium came in existence, since this is such an intriguing topic. And then Beckman later developed an optimization formulation to describe user equilibrium. Beckman formulation has been used to prove that user equilibrium is a convex optimization problem. So the work done by Beckman kind of ties the transportation engineering to operational research, where we have changed a transportation problem, which is this kind of shortest path user equilibrium problem, into a convex optimization problem, which is more of a mathematics and operational research side of problem. Now, using techniques available in operational research field, we can solve this convex problem to figure out the link flows. The convexity of user equilibrium allows the formulation of algorithms to converge to the equilibrium flow. System optimal um optimization is a non-convex optimization problem. So user equilibrium can be mathematically changed into convex optimization, and when we try to do the same thing for system optimization, it turns out that system optimization is a non-convex problem, which means there may not exist a unique solution when we are trying to solve system optimization. So when we are trying to solve user equilibrium, since it's a convex optimization, it will converge to a single solution, or within that convergence criteria. But system optimization might not converge to a problem, so converge to a solution. So what it means is, when we are looking at user equilibrium, the solution would likely oscillate and converge to a number, whereas when we are looking at system optimization problem, usually the solution can oscillate, and then it will likely keep oscillating towards the end. So Frank-Wolfe proposed a convex combination method in 1956 to solve the quadratic programming problems with linear constraints. So most of the travel demand models were developed in 1950s and 60s. We still use it to this date. These are well thought through mathematical work that has been done in 1950s to 1970s. Most of the mathematics we used in practice in traffic operation were developed in this time. And then most of the work we do is basically implementation at a larger scale and how to handle codes and stuff. But the fundamentals for most of the work we do in traffic were developed well back 50 years ago. So Frank-Wolfe algorithm was later used to determine equilibrium flow for the transportation network. A great resource to understand the mathematical formulation. Let me change the color here because this is important. A great resource to understand the mathematical formulation related to transportation network is this book, Urban Transportation Network, Equilibrium Analysis with Mathematical Programming Methods by Yusuf Sefi, who is a MIT professor. So this is how I got introduced to transportation engineering and traffic assignment. And this is one of the greatest book I have read in my career. It's called Urban Transportation Network. It's a kind of a written from a mathematical or uh, operational research perspective, which ties into transportation system. So this gives a background on some of the operational research concepts that are needed for us to understand the traffic assignment and other concepts related to transportational research. So this is one of the great book. If you are looking for something challenging, something interesting to read, I would highly recommend to read this book. This book used to be freely available. when I was student, and later on I have a printed copy from back then. Right now I recently noticed this is a paid book now, but it's definitely worth it. This is my personal favorite book. uh, is well written by Yusuf's Sefi, or just Sefi. He is a professor at MIT, like most of the brilliant minds. He's a professor at MIT, and kind of pretty thankful for this book and him to introduce me to the exciting field of transportation, just beyond a little bit of political environment and all those things. So we will look at the practical side of things, and we look at local preferences, and throughout the videos we will see how different factor affect our kind of solutions. But here we are talking about pure in terms of mathematics, logic, and reasoning, and this is a great example on uh, what mathematics can do and where it can lead us. So there are several other, I will switch back to blue color. There are several other developments in the algorithm since then, such as by conjugate frank-Wolfe algorithm. So it's a frank-Wolfe algorithm, but we are trying to converge from both sides, which converges faster than original frank-Wolfe algorithm. By conjugate frank-Wolfe is widely used in practice to determine equilibrium network flow. So most of the travel demand models are based on by conjugate frank-Wolfe algorithm. Frank-Wolfe algorithm works by iteratively shifting a proportion of flow from routes with higher travel time to the route with shorter travel time. So the way Frank-Wolfe algorithm works is, first, let's say these are origin, destination, and there are three routes. So first, all and nothing assignment is done. So all the trips, let's say there are 100 vehicles, are assigned to the shortest route. Then the travel time on this route goes up. Then another route becomes shortest. Then some part is shifted to that route. Then the travel time on that route goes up. Then the new route becomes the shortest, and then some of the volume is assigned to this new route, until this process is repeated until all the travel time on all the used path becomes the same. So this is in general like Frank-Wolfe algorithm. Now the important thing is how much volume we are going to shift, and that's where all the logic plays in. So we cannot keep shifting back and forth uh, to solve this problem. So these are some notations that are used in explaining Frank-Wolfe algorithm. Let's say L is the link, QL is the flow on the link, TL is the travel time, which is a function of flow. As we remember from our previous presentations, usually is given by an exponential function like this. It's called BPR function, and given by T. This is covered in chapter 2 under travel time. T is equal to T naught 1 plus alpha, uh, 1 plus alpha volume by capacity to the power beta. So that's the BPR function. In this chapter, when we are looking at practical implementation, we will look at what are these alpha and beta values are and how they are determined pretty soon. Then this is the travel time on link, which is a function of flow. TL is the current travel time on the link. Lambda is the step size that is used in convex combination method, and is also used to figure out how much volume we are gonna shift from the higher route with higher travel time to the route with shortest travel time. Lambda low and lambda high are temporary. So important thing is temporary low and high values of lambda used in bisection method, and f is value of Bachmann objective function which we are trying to minimize. So step 1 is to initialize. During initialization, what we do is we first find the shortest path between origin and destination node based on free flow travel time. So let's say we are working with empty network and we are trying to put some demand between origin and destination. So initially, first we assume that the travel time is free flow travel time, or if the net we are already done with different other ODs, and then we will calculate the travel time based on the other ODs as the base travel time. So assign all the demands onto the shortest path. Initially we assign everything to one single path, and then assign all the demands onto shortest path. I mean, this step is also called all or nothing assignment. So the way frank-Wolfe algorithm work is by iteratively using all and nothing assignment, trying to figure out the shortest path and then assigning all the volumes to the shortest path. This is called all and nothing assignment. Update travel time on all the links. So based on the traffic volume assigned, we typically update all the links even though the volume is 0 and the update may not be needed. It's faster to just go through all the links and update them. Recalculate the shortest path and perform all and nothing assignment one more time. This would generate a temporary set of flows. So what we do is we figure out the next shortest path and assign all volume to it. So let's say I have 3 paths here, and this is my origin and this is my destination. Let's say initially this was my shortest path, so I assigned 100 volume to it and the travel time went up. And now let's say this is my shortest path, so I will temporarily assign 100 volume to it, but temporarily. And then what we will do is we'll figure out the step size to go from here to here. So temporarily this link has the volume 100 on it, which is given by this q-l. Calculate the optimal step size lambda to move from this 100 to this 100. So what we are trying to do is we are trying to transfer this 100 completely on top of the next shortest path, but we will not completely transfer it. We will transfer only a proportion of it. That proportion is known as step size, which is given by lambda. So what this 100 dash represents is complete transfer of this number 100 onto the new shortest path. So what, when we are looking at this 100 dash, we are looking at a system like this. So we have 100 vehicle here temporarily this becomes 0 and this becomes 0. So that's what 100 dash represent. Currently we have 100 vehicles on the main one and 0 on the top and 0 on the bottom. Let's say there are 3 routes within OD pair. So we use the bisection method to figure out what is the how much volume to shift. So set the lower proportion to 0, higher to 1, take the lambda as the average of them and figure out the derivative at the value of lambda. So the derivative of objective function is given by this equation. In this equation, once lambda is known, q is known, q dash is known, so and then we sum it up for all the links, and that's the derivative of objective function with respect to lambda. To avoid the confusion, I should have put the lambda on this side. So set the lambda low is equal to lambda and set lambda high is equal to lambda. It's kind of throwing me a little bit off. So we are setting the lambda low is equal to lambda if derivative is negative, and we are setting the lambda high to lambda if the derivative is positive. So I should have put it on the right hand side, but kind of in code it works the same. And then if lambda high minus lambda low is lesser than a threshold, then a convergence is reached and then stop, and lambda is equal to average of lambda high and lambda low. So we might end up with lambda high and lambda low very close to each other, and that's when convergence is reached. So update the link flow. QL is equal to original flow plus lambda, which is the step size, which we just figure it out from here. So after step 2.6, what we are getting is the lambda step size we are going to move. And then once we know the lambda, we move some flow to the other route. So initially we had 100 vehicles here. Let's say my lambda is came out to be 0.1. Then we will move 10% of the volume to the next one. So in the next iteration, what we will have is we will have 90 vehicles left on the, let's say these are 3 routes, so we will have 90 vehicles left on the middle route and 10 vehicles on the top route. So that's the property of what lambda does, and we'll keep doing it until the travel time criteria is met. An essential aspect of finding user equilibrium is determining the shortest path in step 0 and step 1. So we'll notice step 0, which is initialization, needs shortest path, and at every iteration we need to recalculate the shortest path to move the volume from the high travel time to the low travel time. So we need to update the shortest path several times. So during convergence, if the step 3 convergence is not met, then we usually go up to the step 1 and then repeat step 1 several times. So in this user equilibrium equations, we are determining shortest path again and again and again. So the shortest path between origin and destination is the path with the lowest travel time. The shortest path is typically computed using Dijkstra algorithm. The transportation network under Dijkstra algorithm is represented using link and node structure. A Dijkstra algorithm is used to find the shortest path between one origin node to every other node in the transportation network. So this algorithm can find shortest path from one origin node to every other node. So let's say there is a system like this, which is a typical example network, and it can find from origin node to every other nodes in the system. The notations used for Dijkstra algorithms are as follows. Each node is assigned a travel time labeled by Ti. So Ti is the travel time for node I. The predecessor node is labeled as Pi. So let's say this node is the part of shortest path, and the predecessor node uh, on the path is denoted by Pi. So a predecessor node is the node through which the shortest path is going to current node. So let's say we are looking here and the shortest path is going like this. Then the predecessor node for this node will be a node here. Both node attributes Ti and Pi are denoted together as Ti-Pi. The steps involved in Dijkstra algorithm are as follows. Step 1 is initialization. Assign each node a travel time of value of infinity. So first we assume all the nodes are infinitely far away from the origin, and the predecessor node of each node as 0, because we don't know any predecessor node and shortest path is not detected yet. Each node is assigned a level of infinity, which is the travel time, and 0 as the predecessor node. Change the level of origin node to 0 and 0. So what we do is we change the level of origin node to 0 and 0 because to go from origin to origin itself is 0, and then as the shortest path going from origin to origin is the there is no predecessor to the shortest path going from origin to origin, so it's 0. As the travel time from origin node to origin node is 0. Create a dynamic sequence list and add the origin node to the dynamic sequence list. So what we do is we will maintain a list called dynamic sequence list. Dynamic sequence list. Next, pick the last node from the sequence list. So we usually add the nodes to the sequence towards the end. So let's say the sequence node has let's say sequence 1, sequence 2. These are different nodes in the sequence list, and when we are adding new nodes, what we do is we add towards the end. So let's say this is the last node on the sequence list. So we pick the last node on the sequence list, say node I. Trace all the downstream node that can be reached from the selected node. For the downstream node, what we will do is we'll go through an example, so we don't have to imagine a lot of stuff. So we'll just go through an example here, which is given here. For a downstream node J, if the travel time is lower than the travel time of predecessor node plus travel time, then update the downstream node level uh, to this node. So let's say this is the node we are looking at, and it can reach to 5 different other nodes. So this is node number 1, 2, 3, 4, 5, and this is the shortest travel time for this node, let's say, is 8. So what we will do is we'll figure out the figure out whether this shortest travel time plus the travel time of this link is smaller than what was the travel time label of this different node. So let's say the travel time on this link is 2 and travel time label on this one was 15. So now 8 plus 2 is 10 and the label was 15. So now we have detected a new shortest path. So what we will do is we'll change the travel time to 10 and change the predecessor node. Let's call this node as node number 10. So ah, predecessor node as 10. Now let's look, let's say the travel time for this one, the travel time level is, let's say, 5 and the travel time here is 1 minute. So 8 plus 1 is 9, which is greater than 5. So we will not update this node at all. So we will still have the travel time as 5 and predecessor node as what it was for node 2. So these things will become more clear as we look through the example. And we will keep doing it until the sequence list is empty. If the sequence list is empty, then stop. Otherwise, go to step 1, which is this, and keep doing it again and again. The shortest path algorithm works when there is only one link between two nodes. If more than one links are connecting two nodes, then a dummy node can be inserted onto one or more links. This ensures that two links do not have same start and end nodes. So one thing to remember is, since we are detecting the predecessor node, there needs to be only one link between two nodes. So if there are two links, we don't know which link to consider for the shortest. So what we do is we insert a dummy node we keep one link as it is, and for other links, let's say there are 3 links, so we can just insert a dummy node onto the other links. Then it becomes a new link system, uh, like a dummy link here. So now the routes are broken into uh, one link here, one link here, one. So 1, 2, 3, 4, 5 links with different nodes. So the algorithm kind of knows which route is taking. This is kind of complicated. When we are actually implementing it for all purposes, we run into this problem, but for academic purposes, we do not need this part. But when we are actually writing an algorithm to calculate the shortest path, we need to consider a dummy node for multiple routes. So let's look at this example. Example 3.4. A transportation network is given like this. These are the travel times. Uh, these are the travel times on the links, and we are not updating the travel time based on flow. So find the shortest path. So the flow is already updated, travel time is already updated. Find the shortest path from node 1 to all the nodes. That's what we are trying to do. So when we are working with Dijkstra algorithm, the flows and travel times are fixed, which are given by these numbers. So the first thing we will do is we'll declare the travel time for all the nodes as infinity and predecessor node as 0, as I mentioned. Then the next thing we will do is for the origin node, we'll declare the travel time as 0 and predecessor node as 0, because the travel time to go from origin to origin is 0. Next, what we will do is we will compute, uh, we will figure out all the downstream node of node 1 and put node 1 on the sequence list. So here during initialization, we will add the origin node to the sequence list. So now my sequence list has 1 in it. In the next step, we'll pick the last number from the sequence list, which is 1, and figure out all the downstream nodes. So this one, and this one, and see if the travel time, which was infinity earlier, uh, is higher than travel time here plus travel time here. Since we are starting with infinity, all of these nodes will get updated. So this node will get updated with the minimum of infinity, which is the previous travel time, and 0, which is coming from here, plus 9. So the new labels for this node will be 1, because we can reach to these nodes sorry, the travel time. So the travel time here is 14 and 1. The update for this node will be the travel time here, which is 9, and predecessor node as 1. Similarly, the update for this one will be the travel time here 7 plus 0, 7, and then predecessor node for 2 will be 1. So that's how the update happens. In the next step, we will choose one on the sequence list. So here we reach 3 of the nodes. So what we will do is we'll add these 3 to the sequence list and take one out because we have already processed one. So we took one out from the sequence list. We added 2, 3, 6 in any order to the sequence list. Now, even though we added it in any order, we'll pick the last one. So we'll take the last one. Let's call 6. So we have selected 6. The first thing we do is remove it from the sequence list. Then we figure out all the downstream nodes that can be reached from 6. In this case, there is only one. And then we look at whether the travel time attribute here is higher than travel time attribute here plus this. So travel time attribute here was 14 plus travel time here is 9, which is smaller than travel time attribute here, which was infinity. So what we will do is we'll update this node with the new travel time. So 14 plus 9 is 23, and update the predecessor node from 0 to 6 because the 6 is now the shortest travel time. Now what we'll do is we'll take out the 6 and then we will add 5 to the sequence list. Now we have 5 here. In the next step we will choose 5, and now there are no downstream node of the from going from 5, so we will take out the 5 in this step. There is no update needed in this step because we cannot go anywhere from 5. Now what we will do is we'll pick the number 3. So we'll pick the number 3 here. There are 2 downstream links. One is here, one is here. Now we'll try to figure out whether they need update. So the travel time for this one was 14 earlier, but if we take the travel time for this node, which is 9 plus 2, 11, which is less than 14, so we need to update node 6. So node 6 will be updated as 9 plus this 9 plus 2, 11, and the predecessor node is 3. Since we updated node 6 will get added to the sequence list. The same goes here. The travel time here was infinity, so we will take the travel time 9 plus 11, add it up to 20, and predecessor node as 3. Since this node is also updated, we will add it to the sequence list. Now we keep doing the same thing. So now we have 6. From 6 we can go to 5. The predecessor node for 5 was was 6, but the travel time was 20. So what we 23, sorry. So what we will do is we will update the travel time, which is the shorter travel time, and then add 5 to the list now and take out 6. Now we have 5 on the list again, but since we cannot go anywhere from the 5, in the next iteration we will remove the 5 because there is no downstream link going out of 5. Now the next one on the sequence list is 4. So we'll take the 4, we'll figure out where we can go with 4, so we can go in this direction. The level for 4 earlier was 20, so 20 plus 6 is 26. Is 26 lower than 20? No. So we do not update travel time and predecessor sequence list and sequence list. So since this 20 is already lower than this 20 plus 6, 26, we do not update this number or the predecessor list. So what we will do is we'll remove 4 because all the downstream nodes are checked, and then there is only one node left in the sequence list, node 2. We will take node 2, try to see whether node 3 needs an update. So there are 2 downstream nodes, node 3 and node 4. So the travel time up to node 2 is 7 minutes, so 7 plus 10 is 17, but node 3 already has a shortest path with 9 minutes, so we don't need to update node 3. Then we check node 4, so 7 minutes plus 15, 22 minutes, but it already has 20 minutes of shortest travel time, so we don't need to update node 4. So 3 and 4 are checked but not updated, so nothing is added to the sequence list, and node 2 is removed from sequence list. Now this sequence list is empty and we are done with shortest path. So at the end of this shortest path procedure, what we did, what we got is this network. So from node 1, uh, we can reach any other node in the network. So let's say we want to figure out the shortest path between node 4 and node 1. What we will do is we will trace the predecessor list. So predecessor list for node 4 is 3, so we will go to node 3. Predecessor node for node 3 is 1, and we will go to 1. So the shortest path between 1 and 4 is this. Let's say we want to figure out the predecessor. Let me reload this. Let's say we want to figure out the shortest path between node 5 and node 1. So the predecessor node for node 5 is 6, which is here. Predecessor node for node 6 is 3, which is here, and predecessor node for node 3 is 1, which is here. So we trace it backwards. So the shortest path between node 1 and node 5 is this. This is the shortest path going from node 1 to node 3 to node 6 to node 5. Also the first value gives the shortest travel time. So this is the shortest path, and if we sum up the numbers, so 9 plus 2 11 plus 9 20, which is given by the first number. So this is how we calculate the shortest path and shortest travel time in the transportation network using a Dijkstra algorithm. We kind of wanted to give the background of a traffic assignment and go through Dijkstra algorithm. I wish uh, we can discuss more on the theoretical side of things, but it's not needed in practice. But it's very intriguing. From my personal experience, these are these are something traffic engineers should read, or if you want to be like a great thinker in terms of traffic engineer, and if you are interested in something where traffic engineering overlaps with operational research, then this book and these concepts are there for you. So I'll just like to close this video by thanking Sefi, who has written this great book, and now it's kind of sold on Amazon, I think, but at the time it was free. So thank you for providing this very good, very good book, a very inspiring book in some sense for free. Uh, so thanks again.